Hi, today in Applied Calculus, we're going to learn about the derivatives of exponential and logarithmic functions. So in our previous sections, we learned the power rule. That was used to take the derivative of functions that were in the form x to a power. In that, our base was a variable and our power was a number. Here, we're going to look at what happens when our base is a number or a constant and our exponent is a variable. And that's what's going to make this different. We can't use the power rule on these exponential functions because they don't have the same format. They're a different kind of function. So first, let's find this derivative of f of x equals a to the x, where a is a constant. And we're going to do it the long way one more time to see what happens and notice a neat pattern in that. So we would take the limit as h approaches 0 of f of x plus h minus f of x all over h. And what does that look like for a function a to the x? Well, remember, we just replaced the x's with x plus h. So that would be a to the x plus h when we're doing f of x plus h. Minus, the function was just a to the x all over h. If we try to take the limit right now, we would get an indeterminate form, 0 over 0. And so we're used to doing some algebra to fix that. Well, the algebra is going to be a little different than other times. So this time, the algebra is going to be dealing with the rules of exponents, since this is an exponential function. We are very good at going from this step the other way, but we don't often recognize this way. Remember that if you're multiplying two numbers with the same base, we add the exponents. Well, that means if you have exponents that are added, you can think of it as multiplying with the same base. So what we see now is both of our terms in the numerator have an a to the x in them that could be factored out. And not just factored out inside the fraction, but actually this limit has to do with h. It doesn't have to do with x. And so a to the x is a constant with regards to the whole limit, way back to limit laws from the beginning of the semester. So the a to the x can come out. And so this is actually as far as we are able to get. We don't really have the skills needed to evaluate this limit, but we're going to look at it a little bit further. What's interesting here is that the derivative of a to the x ends up having a to the x in it. And that's neat and different than anything we've seen before. So we got to figure out what's going on with this limit part, but there is at least some part of the derivative of this exponential function that is itself. It's the original function that we had. So we're going to look into that a little bit more. What does this mean? If, for example, a was 2, then our derivative would be 2 to the x times this limit as h approaches 0 of 2 to the h minus 1 over h. Again, we don't really have the skills to solve that other than to do it numerically with a table, and I've done that work for you. So in this case, that limit works out to be about 0.7. Or what would it look like if our base was 3? If our base was 3, then the derivative, based on the limit definition we just did a second ago, would be 3 to the x, limit as h approaches 0 of 3 to the h minus 1 over h. Again, I've done the work for you for what that limit works out to be, and it's about 1.1. So when our base is 2, that limit works out to be a little bit less than 1. When our base is 3, that limit works out to be a little bit more than 1. And since the derivative is a multiple of itself, it has, for instance, that 3 to the x in it, or that 2 to the x in it, wouldn't it be neat if the limit part worked out to exactly 1? And so we're going to find out when that happens. So if this limit worked out to be exactly 1, then we'd have a very nice derivative. So it turns out that there is a special number between 2 and 3 where that limit would work out to be exactly 1, and that number is e, right? So e discovered by Euler, which does start with the e despite how it sounds. And it turns out that e is the number where, when you take the limit as h approaches 0 of e to the h minus 1 over h, you get exactly 1. So you've probably dealt with e at some point in past math or science classes, and it does go on forever, right? This is just an approximation. So it's like pi. It has its own symbol, but it keeps on its non-terminating decimal there. So what does that mean if e is our base? Well, we said Whatever this number is, and this is the number e, the derivative is itself e to the x, we saw that when we did some factoring, times this limit where e is our base in that, and now we know that the limit is 1, and so it turns out that the derivative of e to the x is exactly e to the x. And that's really special. That's different than anything we've done, and so it's the coolest derivative ever if you ask me, and the easiest to remember. So e to the x specifically, we'll have to be careful when we have something more complicated than the x in that exponent, but e to the x is its own derivative. So the derivative of e to the x is e to the x, and it came from that limit definition work that we did. That's not something you have to show to me, but I wanted to show you where it all comes from. So let's try taking some derivatives. You should find that it's very nice. All our other rules about sum and difference and constant multiples, they have not changed. So that 3 is being multiplied by our function of x. And if you want, you can show some extra steps, but you'll probably get to where you don't need to. So that 3 is a constant that can stay and get multiplied by the part with the x in it. But what is the derivative with respect to x of e to the x? It is just e to the x. So I really did take its derivative. It's just that it's its own derivative. So absolutely, if you can go straight to that step after some practice, that is more than fine. Okay, so now we need to be careful in part B, because you see that I have multiple kinds of functions mixed together, and we have to be conscious of which kind of function we're dealing with. 5x cubed, that's the old power rule. That's a variable base with a number constant exponent. So is 3x squared, so is 11x, and so is 14. It's a constant. And then inside, mixed in with those, is a numeric base. It might look like a variable to you, but it is a number. 2.71 keeps going, right? Just like pi is really a number, even though it has a symbol. So that's a constant base raised to a variable. So that's going to be a different rule. So we're going to go term by term and just make sure that we use the right rules for the right kinds of functions. So our derivative is power rule here, 15x squared. Remember, I'm bringing down the power, multiplying it by any constants that were already there, and then subtracting 1 from the power. Here, the 7 is the constant that can stay, and I really did take the derivative of e to the x, but it's its own derivative, so it's e to the x. Here, then minus 6x with the power rule, plus 11 with the power rule, and the derivative of 14 is 0. You don't really need to write it, but I want to show you that I went term by term and stated each derivative. So it's by no means difficult. We just have to be careful now that we are mixing together power rule problems with this new e to the x rule that we have. And so here's one more, and there's one more thing we want to watch out for as we do this. So as we go to take the derivative, this is x to a power. That is the power rule. We get 6x to the 5th. Also x to a power. That is the power rule. Now here is where we have to be careful. So this is e squared. If you were to type that on your calculator, e squared, using the e button, you would get a number. You would get whatever 2.71 squared is. And so this is a number. This is a constant. And what is the derivative of the constant? It is 0. So I obviously don't need to write a 0, but I want to show you where everything came from. So watch out for that. Another way to think about a constant is a term that doesn't have your variable in it. So there is no x in that. If it doesn't have your variable in it, then it is considered constant with respect to that variable. But that is an actual number. You can type it and get it on your calculator. So watch out for those. And then here, this is power rule, minus 1. And now this one does have an x in it, and the derivative of e to the x is e to the x. So again, I just went term by term, but that is one more thing we need to be careful of. And we need to be careful that we are not trying to do the power rule with e to the x. It is not x e to the x minus 1, because it's not the same kind of function. It is a constant base and a variable exponent, not, as the power rule does, a variable base and a constant exponent. So it has its own rule, and it's a really easy rule. So don't make it harder than it is by trying to use the wrong power rule on it. So also in these sections is a little bit of review of E and ln. And so one of the things that we will eventually be doing problems with once we have a little bit more knowledge in later sections is some applied problems with compound interest. So in the past you probably did interest compounded annually, monthly, that sort of thing, and you had one formula, and then you did interest compounded continuously. So I always told my students in classes where we were learning both of those formulas, right, continuously is the one that has the E in it. So the formula for that, as you may remember, is A equals PE to the RT, where P is the principal or the initial amount that you put into the account, T is time in years, R is the annual interest rate, and this is really important. We absolutely must write that interest rate in its decimal form. So to be clear, just because a percentage rate has a decimal in it, that does not mean it's in its decimal form. We still have to actually move that decimal point to get it from percent to the decimal form. And then A is the result, right? A is the amount that you have in the account if you invest P dollars for T years at an interest rate of R. So it's how much you get out of the account after time has elapsed. P is how much you started with in that account. So this is actually no calculus whatsoever. Again, we'll talk about this, but because of the interest rate, we can't actually take derivatives with these quite yet until we learn another rule called the chain rule. But this is the time while we're learning E's and LNs to kind of recap this so you're ready when we get there. So this says an investment of $5,000 earns interest at an annual rate of 5.39% compounded continuously. So as we read, the compounded continuously is what tells us that we are using A equals PE to the RT. That is a formula that you are going to need to know and that will not be provided. And then we are supposed to just write a function. So as we read through, we need to identify. Now we know what variables are in play, so now let's find them as we read. An investment of $5,000. That's how much we started with. That is our P. Earns an interest rate of, now we need to be careful here that we don't say that is R. R is its decimal form. So 0.0539 will be our R, and then our time. So right now we don't know a time. We are just using T because we're writing a function after T years. So the amount in the account after T years will be 5,000 E to the 0.0539T. That is all I am asking you to do in Part A. That is something that I will often do on tests to help set you up, whereas maybe in the homework the very first thing is to go ahead and use it. But that's really a hidden two-step problem. You have to know what you're working with before you can start plugging into it. So right now we are supposed to still have T's in it. Then in Part B, when it says find the amount in the account after 3 years, that means that T is 3. If we go back, right, it said T years, so we know that number of years goes in for T, and all we're going to do is plug in 3 for T. So we have to be careful with the typing here because if I type it like that, I might get into some trouble. So let me remind you in terms of typing on a calculator what this should look like. So you should type 5,000 times, and it's like a star on your calculator, E to the parentheses. 0.0539 times 3. So I wrote it this way because a lot of students will write it that way too. We can use parentheses as multiplication. And then when I say don't forget the parentheses in your exponent, they'll say I have them, see? But they're not the parentheses that we need. The parentheses that I'm talking about are around the whole exponent to say that all of that stays up in the exponent. So if you get some crazy answer that after leaving $5,000 in for 3 years, you get out $1 million, you should know that something's up. if you just typed 5,000 times e caret with no parentheses, 0.0539 times 3, that will raise the e to the 0.0593, but then the 3 would go multiply the whole result, and you get something very different. So please make sure that you are typing e caret parentheses, and then, yeah, if you use parentheses for multiplication in addition to these instead of a star, that's fine. But that's what you should be typing on your calculator, really, regardless of which calculator you have out of the 3 that are permitted. Okay, so that is just a review. Here's our function, and we're just plugging a number in. This is still a review. In fact, it was a question on my pre-calculus test, right? So how long will it take for the amount in the account to double? So they are telling me the amount, A, and they don't have a number, but they want to know how long it would take to double. Well, that would be 2 times 5,000 or 10,000. The question words tell us what we're solving for. How long means I don't know t, okay? So we will have that the amount in the account, right, this is A equals P, well, actually, we already know that it's 5,000, don't we? 5,000 e to the 0.0539 t. So I now know A, and I am plugging in, and I don't know t. I'm trying to solve for t. So it's just algebra, pre-calc kind of stuff. So the order of operations is often an issue for students. We're trying to get to the t. We absolutely must first isolate the part with the t in it by dividing. So you have to divide first, and what you should notice is that even if I didn't know the amount in the account, if it said double, this is going to happen every time. When I divide, that's going to be a 2. So I have 2 equals e to the 0.0539t. And then now I need to get t completely by itself. Well, if it's stuck up in an exponent, then we need the inverse of e, which is ln, the log base e, to undo it. So that's going to be the last step there, is to take the ln of both sides. And ln is the inverse, so it undoes the e. So over here we have ln of 2, and over here we have 0.0539t. And our very last step, because the ln and the e undid each other, is to divide to get t completely by itself. So no calculus here, all algebra and pre-calculus. Just a review. All right, so again, we have to be a little careful with how we type. We need to do ln of 2 and close that parentheses on the 2, and then divided by 0.0539. So when you do that, you should get that t is about 12.8, 12.9 years. So that says that if you invest $5,000 at 5.39% compounded continuously interest, then you can get that money to double in 12.9 years. So hopefully that will help you. There's a little bit of review in there, and then we'll be able to do some calculus in addition to these in a few more sections. So then we also want to talk about the derivatives of logarithms, and the proof of it, to kind of show you why it is what it is, again, involves that later section on the chain rule. So we can't really prove it yet. I hate just saying it is this, go with it, but I can come back and prove it to you later. So the derivative of ln of x is 1 over x. And there's a couple things to note here. The derivative of ln does not have an ln in it. And also, looking forward, I want to make sure you actually think of it this way. The derivative of ln of an inside is 1 over that inside, because we're not always going to end up having an x in there down the road as we continue. So we now have another derivative rule we can apply. But before we do, there are some times when we can use, again, a review from pre-calculus, to make a problem that would be complicated easier by first using the laws of logs from algebra and pre-calc to simplify it before taking derivatives. So we're going to recap those and then we'll put it together to take some derivatives. So there's actually 3 laws of logs that you learned. There's only 2 that are going to be really pertinent in helping us here, so that's why I have those 2 here. One of the laws of logs was that if you have the whole inside of a logarithm raised to a power, that power can come down in front and be multiplied. And so that actually comes from the other rule that I didn't write here. It's actually just a summarization of what happens with the multiplication rule when you have multiplication inside of a log. So that is one of them. Then the other rule that might come into play here is when you have division inside a single log. You get the log of the top minus the log of the bottom. So we have division within a single log, and it becomes subtraction of 2 different logs where the numerator always goes in the first logarithm and the denominator always goes in the second logarithm. So what we're going to see is that sometimes we want to do this before ever taking derivatives to then make the derivatives easier. So A is just a good old constant times it. So again, if you want to show the extra work with that constant rule, you can, but essentially the constant gets to stay and get multiplied by the result of the derivative, and we just learned that the derivative of ln of x is 1 over x. So it's 5 times 1 over x or 5 over x. So that's a very straightforward example. Also B is going to be, but what you can see is that I have it mixed in with one of our other rules. This needs the power rule, 8x squared, whereas this has an ln in it, so it needs the ln rule for derivatives. All right, so the derivative with the power rule here is 16x. Then the 17 is a constant that can stay and get multiplied by the derivative of ln of x, which is 1 over x. So you can dive right in and write that, or you may have even written it this way. And of course, they're equivalent and either one is fine. Okay, so then we're going to get into some where using those laws of logs can help. And that's because actually right now, we can only do these problems if we use the laws of logs, because we do not have a rule for ln of x to the 4th. We only have a rule for ln of x, meaning 1x to the 1st. If it's anything more complicated than that, we either need to use a law of logs to simplify it, or we need a few sections from now, and we're not there yet. So what we're going to do is rewrite first. So notice, and this is going to be important in keeping up with your own work, that this is still y equals. I am not saying y prime because it's not the derivative yet. I am just rewriting it, and we're using that rule that says that if you have the whole inside of a log raised to a power, the power can come down in front. Now be very clear, that is not me using the derivative power rule. It has nothing to do with that. You learned it 2 classes ago, back in Algebra 2, probably before pre-calculus. So this is a law of logs. I am still equal to y equals. I have done no derivatives. I just rewrote the piece that didn't need anything done to it. I literally rewrote it. Whereas here I rewrote it using some algebra. Now I'm going to take the derivative, now that it's rewritten in a way that I know all the rules I need to take this derivative. So the 4 is a constant that gets to stay and get multiplied by the derivative of ln of x, which we just learned was 1 over x. And then the last term needs the power rule. So you could write that as 4 over x minus 4x cubed, or leave it that way. But we did need to do this rewriting still as y equals before then taking the derivative y prime. So you can see there's something similar here, but there's one other thing to look at now as well. So we are going to rewrite first. It's y equal, it's still the original. Again, I don't have a rule for ln of x cubed. I only have a rule for ln of x. So I'm using that law of logs to bring the 3 down in front of the ln. The e to the x I don't need to do anything with. I'm just rewriting the original function. But there's something I can do here. And we just did it as part of our review with our financial problem. So remember that ln and e are inverse functions and they undo each other. And so ln of e to the 4th is actually just the number 4. I didn't do any derivatives. I am using algebra to rewrite the function. Now I'm going to take derivatives, and it's going to be easier for two reasons. One, it was impossible for me to do this before because I don't have the other rules I would need to do it, and this just made it easier from an algebra standpoint. So the derivative now, 3 is a constant that could stay and get multiplied by the derivative of ln of x, which we just learned was 1 over x. And then this is a different kind of function, so it has a different rule. It is an exponential, and we learned that the derivative of e to the x is e to the x. So I really did take its derivative, but it's its own derivative. It's the coolest derivative ever. And now the derivative of a constant 4 is 0, right? So I don't need to write that, but I want to show you that I took the derivative of each piece. So I could summarize all of this and have 3 over x plus e to the x is my derivative. And then the last one, e, is when we're going to get to use that other rule that we recapped from laws of logs. We need to be careful with the 9 as well, though. So first we are rewriting, and we might take a couple steps to do that. So when we go to use the rule that says we do ln of the numerator minus ln of the denominator, I have to be careful because the 9 was getting multiplied by the whole thing. So now that there's going to be two terms, I need parentheses to say the 9 goes with each of them. So we're going to have ln of the numerator minus ln of the denominator. No calculus whatsoever. This is just rewriting with algebra laws of logs. And so you may want to go ahead before you ever take the derivative and distribute that as well. And now we are able to take these derivatives. But we have to be careful because this is similar to something that came up with e's a little earlier. There is no x in that at all. And so it is a constant. If it doesn't have your variable in it, it is a constant. Also, you could type this in your calculator. Type 9 times ln of 10, and you'll get a number. And the derivative of a number or a constant is 0. So now I'm actually taking the derivative. So now I have y prime. Here it was y, not y prime. Now it's y prime. And that derivative of that is 0 because that was a constant. But then over here, we can take the derivative. So if you forget to write this, you don't have to write a 0, but then some students forget about this sign. So don't forget there was a minus there. The 9 is a constant that stays and gets multiplied by the result of the derivative of ln of x, which is 1 over x. So our derivative is negative 9 over x. Okay? So both of those, we have looked at exponentials and logarithms when the base was e, and things really worked out nicely because the base was e. What if our base is something other than e, any other number? So it does still have to not be 1 and be greater than 0, but maybe it's 3 or 2 or 7 or 2.5 or something like that. And so since we would have had that, we had said a to the x times some limit, and we said we didn't know what that limit worked out to be. Well, it turns out that that limit works out to be ln of that base. So we're using b here, just b for base. So this is another rule that you are going to need to know. If your base is not e, although I'll show you that it works for everything, then the derivative is still neat. It's still itself, but then times ln of the base, okay? Now notice that if your base were the number e, this does still work out, because if it were the number e, we'd have e to the x times ln of e, but ln of e is 1. And so really this rule encompasses everything. It's just that e is so nice that it's kind of nice to keep it separate, that you can get that derivative really fast. Similarly for logs, ln is the short way of saying log base e of x, and its answer was 1 over x. Well, if your base is something other than the number e, then you still have that 1 over x, or 1 over its inside part. So remember, this is of x, the x is the inside. But you have, again, the extra limit part you would have there turns out to be ln of the base. So in this one, the ln of the base lives in the denominator with the x. If your base was e, you'd have 1 over x ln of e. Ln of e is 1. So this does not conflict with the ones we already know. It actually encompasses them. It's just that ln and e are so nice that it is kind of nice to remember them separately. So we're going to do a couple using those rules. So if you have 3 times log base 4 of x instead of base e of x, which we would have usually written as ln anyway, the 3 is a constant that stays and gets multiplied by the derivative of the part with an x in it. And we now have a rule for this. So this is 3 times, and so it is 1 over the inside x times ln of the base, and the base was 4. So I could, if I want, put all this together and have 3 over x ln of 4. So that is another derivative rule that you will need to know. Flashcards are great for these. And I will also have a nice summary sheet where all this is on one page for you as you study too. And then the other rule that we just learned is if instead of e to the x we have some other number, in this case 23, then the derivative is still itself. So it's itself, but then there is this times ln of the base. And that's the only difference. So we're just plugging straight into those two formulas that we just learned. So for our last example, we are going back to ln's and e's. And I just want to show you this equation of the tangent line is going to keep coming up throughout the entire course. Just as we learn new functions that we know how to take the derivatives of, then we'll be able to now do it where our function has that in it. So in this case, it's an ln. So it says find the equation of the tangent line to the graph of this function. Now we're going to have to be careful when we get into this because we only know ln of x, not ln of x to the 8. So we'll have to use one of those laws of logs. But remember, in general, for an equation of a tangent line, or really the equation of any line, we need a point and a slope. And then we write the equation. So for the point, remember we always use the original function to get the point and the derivative function to get the slope of the tangent line. So derivative. So we are going to plug the given x value into the original function to get the point. Okay? So here we have ln of e to the 24th, because when we have a power raised to a power, we multiply our exponents. Ln of e, ln and e undo each other, and we get the number 24. So that might look like it's a really ugly point to you, but it actually works out pretty nicely and is the number 24. So this is our point. Of course, it's not my final answer, but it's a key thing that I need. Now for slope, because it's specifically the slope of the tangent line, the slope of the tangent line at a point is the derivative at that point, so now I need the derivative function. So remember that first we have to rewrite this because we had ln of x to the 8th, and we don't know how to take its derivative. So we need to rewrite it as 8 ln of x. That is not me doing anything with derivatives at all. It is not the power rule. It is a power rule about logarithms that you learned back in algebra class. So this is still original function equals. Now I'm going to take the derivative. So our derivative would be 8 is a constant that stays and gets multiplied by the derivative of ln of x, which we learned was 1 over x. So you could write that, or you could write 8 over x. And now to get the slope, I need to plug the given x into the derivative. So the given x into the original to get the y, the given x into the derivative to get the slope. So we have f prime of e cubed equals 8 over e cubed. So that is our slope. Those are the two things that we need to write the equation. Then you get to use your favorite method for doing that, whether that be y equals mx plus b, or the y minus y1 equals m times x minus x1. So now the third thing we need to do is write the equation. So we have y minus our y equals our slope times x minus our x. And again, this will work out better than you might think because of what happens with these e cubes. So we have y minus 24 equals 8 over e cubed x minus, when we distribute the e cubes will cancel and we just get an 8. So last step is to add the 24 over. And so we'll have plus 16. If you were to graph the original function ln of x to the 8th and graph this line, 8 over e cubed x plus 16, and look at the point e cubed comma 24, it should be a point that they share, and you should see that this line rides alongside the curve and does not cross through it. Still an equation of a tangent line. It helps us describe the slope, because that is a number. If you plug it in your calculator, you get a number, how steep this function is at that point. So that is it for both kind of a review of some things with e's and ln's and exponentials and logs in general. And we now have 4 new derivative rules. We have the rule for e to the x and ln of x because they were the nicest cases. And then we actually learned the rule, 2 more rules that encompass those 2, and that is if our base is anything else other than e. So any number a or b, whatever you want to call it, to the x, we have a rule for, and log base any number, not just log base e. Log base 4, 7, whatever of x, we have a rule for that. So we have 4 new derivative rules. Make sure that you practice with them and make sure that you really focus as you go term by term on which rule you're needing. What we made sure to see from the very beginning is that it won't always be that you're only using this rule for this problem and only this one for that problem, that each term could need a different rule in there. All right, and we're getting closer to that chain rule that will help explain some other things as well.